Alright guys, welcome back. This is our second video in the matrix algebra series. So what we're going to look at in this video is matrix multiplication, which you've had some exposure to, but I think some of you are still a bit confused. It might take a while to wrap your head around, so we'll go through that. The identity matrix and the inverse of a matrix. Again, write down your questions because I want you to come to class with maybe 2 or 3 questions that you have about the video. Okay, so matrix multiplication. We know, we've talked about a lot, if you want to multiply A and B, we really need to look at the order of the matrix. So in this case, we have an M by N matrix and an N by P matrix. So that's A and B. So in order to be able to multiply two matrices in this order, so A times B, the two inside elements need to be equal. So the number of columns in the first matrix need to be equal to the number of rows in the second matrix. And this is really important. If they are not equal, we cannot do the multiplication. So when you're doing questions, first off, look at the order. Don't assume that it's possible to multiply just because they've asked you a question. It could be a trick saying, and that you need to notice that actually these two numbers aren't equal, which means I can't multiply. I actually can't multiply these two. In this case, we can because N and N, and so our resulting matrix, we look at the outside numbers. So A times B is going to be an M by P matrix because of that. So that's how we know, first off, if we can multiply, is these inside ones, and then what the resulting matrix is going to look like with these outer ones. So for example, first with our numbers, if we have this matrix A, B, C, D times W, X, Y, Z. So what we need to do is look at, first off, we need to do row 1 times column 1 in the second matrix. So that's going to give us A times W plus B times Y. What I might do, I'm not going to write the times because we do have an X up here and I don't want you to get confused. So we're just going to write AW plus BY. So that is our blue. For the next element, I'm going to do row 1 again of my first matrix times column 2 of my second matrix. So that's going to give me AX plus BZ. A times X plus B times Z. So that's going to give me this one. So that is my first row done of my new matrix. So then I'm going to go C times D, sorry, CD times WY. So I have CW plus DY, which is my green one. And then finally, we'll go purple. I'm going to go CD again times XZ. So that gives me CX plus DZ. Hopefully that's sinking in for you. Some of you that would be very familiar. So now we're going to try a real example over here. So I have 1, 2, 3, 4 times 5, 6, 7, 8. So those are my two matrices. So this here is a 2 by 2. Into a different colour. This here is a 2 by 2. This here is also a 2 by 2. And we know these two are equal, therefore we can multiply. And the outside numbers are 2 and 2, so we're going to have a 2 by 2 matrix as a result. So what we're going to do, we have the first row times the first column. So 1 times 5 is 5, plus 2 times 7 is 14. Then I'm going to do my first row and my second column. So 1 by 6 is 6, plus 2 times 8 is 16. Now I'm going to go with my second row and my first column. 3 times 5 is 15, plus 4 times 7 is 28. Then my second row and second column, 3 times 6 is 18, plus 4 8s are 32. So then I add these and I get 5 plus 14 is 19, 6 plus 16 is 22, 15 plus 28 is 43, and 18 plus 32 is 50. So hopefully, again, that is making sense. If not, definitely write that down as a question to ask. So now what I'm going to look at, very important. So before we had 1, 2, 3, 4 times 5, 6, 7, 8. Now what we're doing is the opposite. We're doing 5, 6, 7, 8 times 1, 2, 3, 4. And we're going to see if we get the same answer because it's really important to know whether the order matters. So in the same way, I'm going to go through 5 times 1, 5 plus 6 times 3 is 18. 5 times 2 is 10, plus 6 times 4 is 24. 7 times 1 is 7, plus 8 times 3 is 24. 7 times 2 is 14, plus 8 times 4 is 32. Frozen. 32. So that equals, well, we got 5 plus 18, 23. 10 plus 24 is 34. This is 31, and this is 46. So this answer here, which we can say is A times B, is actually not equal to this, which we can call B times A. So a very important thing to note is that, let me put it in a different color, AB is not necessarily equal to BA. There may be some circumstances that that is true, and you might want to have a think about those and see if you can find them. But in most cases, they're not equal. So it is really important that you really check out the order that you're using. So that's matrix multiplication. Now we are going to look at the identity matrix. So the identity matrix is something that we define so that if we have A times I, which is the identity matrix, it would be equal to I times A, which would just be equal to A. So it's almost like if A was a number, it's like multiplying it by 1. But I is a matrix. So this is what we identify I as. this is a 2 by 2 identity matrix, okay? And you can get identity matrices for the other orders as well, and you might want to have a think about what they might be, whether we just keep going with the ones on the diagonal. What do we do in that case? So I'm not going to go through the proof now on the video, but that's something that we can do in class to talk about how we know that this is the case. But this part here is really important. This bit here. So any matrix times the identity matrix, so the corresponding identity matrix. So we're saying that A is also a 2 by 2 matrix. So if you have any 2 by 2 matrix, if you multiply that by the 2 by 2 identity matrix, you end up with this same number. So if I had 1, 2, 3, 4 times I, the answer will be 1, 2, 3, 4. And that's something that you can check if you don't believe me, but you should always check. Don't assume that I'm telling you the truth. So now that we know about the identity matrix, which, like I said, we can go through the proof in class, or you could give it a go by yourself. That would be cool too. Now we're going to look at the inverse of a matrix. So unfortunately, we can't actually divide one matrix by another. It just doesn't work. So instead of dividing, what we do is they've come up with what they call the inverse of a matrix. Or it's called the multiplicative inverse of A, this here. A to the minus 1 is how we write the inverse of the matrix A. And we define it as saying A to the times the inverse of A is equal to the inverse of A times A, which equals I. So it's going to equal our identity matrix at the end. So if you, again, think of it as if A equals 2. So the inverse of 2 equals 1 over 2. So 2 times 1 over 2 equals 1. Obviously, we are working with matrices. We're not working with numbers, but that is almost like a number equivalent. That's, to me, that's something that helps me to understand what's happening there. But I'm not going to leave that there because we're not actually talking about numbers. So the inverse, how do we find the inverse? So there's a couple of steps. So we're going to do it without numbers. We have A, B, C, and D, and I want to find the inverse of A. The first thing I need to do is find what we call the determinant. Determinant of A, which you'll be familiar with that word from your quadratic functions. So we call that, that's how we write it, the determinant of A. And that is equal to A, D, take B, C. Very important. So the determinant of A, there's a few ways we can write it. We could also write it as det A. That might be what it says on your calculator, or it could be determinant of A, B, C, D. So you can see it's like saying these two minus these two. Is this up here? So once we've found the determinant, A to the minus 1 equals, I'll write it first and then I'll talk about it, D over the determinant, AD take BC, minus B over the determinant, AD take BC. Minus C over AD take BC, and A over the determinant AD take BC. So that is our inverse of A. So if we know what A, B, C and D are, we are cheering. We can just plug all those numbers in and find our inverse. So this looks a bit tricky, okay? There is a trick to remembering it. So we have our determinant. So we know that det of A, the determinant of A is AD take BC. So if we remember that, we know that this here is on the bottom. We divide all of our numbers, every element, by that determinant. As for the numbers up here themselves, what you might have already noticed, because you have keen eyes, is that D and A have swapped place. Normally A is up here, D is down here. Then I have B and C are in their right places, but they're negative. So the little rhyme I want you to remember is swap, swap, minus, minus. Okay, I promise you, you will remember that for as long as you live. Swap, swap, minus, minus. So if I have A equals A, B, C, D, and I know that I want to find A to the minus 1, I'm going to go, all right, I know what, because Elise told me this in year 11, swap, swap. So my first diagonal, I'm going to swap them. And minus, minus, my second diagonal, I'm going to make them a negative. Then, after that, I divide by the determinant. So I swap, swap, minus, minus, then divide all of these by the determinant of A, which is AD take BC. So that might have felt like a lot of information, but I promise you, swap, swap, minus, minus, that got me through year 12 maths. So that is how we find the inverse of a matrix. So what I want you to do now is have this written down, A to the minus 1, multiply A, B, C, D by, also multiply A by A to the minus 1 and see what you get. See, what are we supposed to get? Do you remember? We are supposed to get this, the identity. Oh, hello. We are supposed to get the identity matrix. So if you multiply A and the inverse of A and you get 1, 0, 0, 1, then well done. We've done it right. Or even try putting some numbers in here and see what you get. But we will be practicing this in class, I promise. So now we look at the laws that we have for matrices under multiplication, which we looked at that for addition. So we have some similar ones for multiplication. So we have A, B, C. So AB times C is the same as A times B times C. Pretty straightforward, but notice how these are still in the same order. Always keep them in the same order. So this is what we call the associative law. So we did have an associative law when we talked about addition. This is the associative law. Then AI equals IA, which equals A. And remember, this was our identity matrix, which is for 2 by 2 is 1, 0, 0, 1. So this is what we call the multiplicative identity law. Multiplicative identity law. When we talked about addition, we had, what was it called? The additive identity law. So now it's just the multiplicative. So this is just the multiplication version. So now we're talking about inverses. So a to the minus 1, so the inverse of a times a is equal to a times its inverse, which is equal to our identity matrix. Now, this is only true if the determinant of a is not equal to 0. So if we come back, if this determinant is equal to 0, a to the minus 1, oh no, okay, a to the minus 1 cannot exist, because we know that dividing any number by 0 is not defined. We can't define that number. So if you'll find, that's why we do this step first. If you're asked to find the inverse and you find the determinant first and you find out, oh, it's 0, then we say, okay, well, in this case, since the determinant is 0, a does not have an inverse. Okay, so that's only if it equals to 0. Otherwise, it's fine and we can go ahead. So, important here, this is true if the determinant of a is not equal to 0, and we call this the multiplicative, I'm just going to write that, multiplicative inverse law. Multiplicative is just too long of a word for me to write on this. Now, A0, so this is the 0 matrix. A0 equals 0A, which equals 0. So this is similar, this is what we call the 0 law. Now with the addition, when we added 0, if this was a plus in the middle, then A plus 0 equals 0 plus A, which equals A, because you're adding 0. But remember, when you multiply by 0, you always end up with 0. So any matrix multiplied by the 0 matrix, as long as they're the same, the order works. So as long as they can be multiplied, this is all assuming that these things can all be multiplied. Okay, then we end up with 0. Here we have the distributive law. Distributive law. So A times B plus C is equal to AB plus AC. And again, very important to note that generally AB is not equal to BA. So when you're rearranging, you might be given something like this. For example, AX equals B. So we're going to say we know that a to the minus 1 exists. We're told that. Find x. So if that's what we're given, we have ax equals b. Now, a to the minus 1, hang on, before I do that, normally if this was just a number, you would bring this a to the other side and it would be, yes I know, we would have b divided by a, but we know that we can't divide, so instead we talk about the inverse. So a to the minus 1a, or ax, come on, a to the minus 1 times ax equals a to the minus 1 B. So see how I put it out the front here? So I've put it out the front here. Very important. And because we know from our associative law, A times AX, I will have a look at it back here. So A times BC is equal to AB times C. So here we have A inverse times AX is going to equal A inverse A times X, which equals A inverse B. And we also know that this equals I. So we have IX equals A to the minus 1B. And we also know that I times anything is equal to itself. Here, IA is equal to A, so IX is equal to X. X equals A to the minus 1B. So basically what we've done is instead of bringing this A over and dividing it, we're bringing it over and multiplying by the inverse instead. But see how because the A was in front on this side, it's in front on the other side as well. So the order is very important. That's the end of this video. Please make sure that you write down any of those questions that you have. Try and come up with at least 2 or 3 things that maybe you don't understand or you have an extra question, and I will see you in class.